Hey guys, this is going to be some notes for 23.1 through I think 23.3 is where we're going to go to. Here in chapter 23 we're going to be talking about optics and how light interacts with geometric shapes and objects like mirrors and lenses, and how the curvature of those objects affects the way we perceive light, how it interacts with different materials. And so the first thing that we need to understand is that when we talk about light and how we model its behavior in terms of reflections and bounces and bending, we're always going to use what we call ray model to represent the direction of light traveling. Now, the truth is, if you look at this picture here on the right of the eye and the pencil, technically we're looking at a lot of different rays of light heading out infinitely many different directions, that we have these rays of light that travel outward, and only some of those will actually come to our eye. Okay, and so it's why something might look a little differently shaped from a different angle, or why colors might be a different hue from a different angle. We're getting different rays of light reflecting off of an object. But we're going to use these straight line rays to be able to model the general behavior of light as it leaves an object and how we perceive it. So a couple of things that we need to understand about reflections. We're going to start with a flat, or what's called a plane mirror. The word plane simply means that it's a flat surface like a plane. And so, when we see this word plane, we're talking about flat. So we have a flat surface, we have a ray of light coming in from some sort of a source. It doesn't matter what that source is. Light's coming in, it hits the surface, it bounces off in a reflected ray. So we have the incident ray coming in and the reflected ray coming out. Now when we talk about the angle of incident or the angle of reflection, as a kid I used to think that I'd focus on this angle down here. This was me early in physics. I was like, hey, these angles, like when you skip a rock on a pond, where you skip a ball, you bounce a ball off of the ground, often I would think about these two angles as these important angles. Well, initially that actually doesn't matter much on a flat surface which angle you're talking about. As long as we could all agree, it's fine. But later on, as we start to talk about refraction, this angle does matter. And so we need to understand that the angle of incident and the angle of reflection are always measured in comparison to what's called the normal to the surface, or perpendicular to the surface. So our actual angles that we care about are always measured against that perpendicular to the surface. Okay, and so it's just important that we all have the same agreed measurement or idea of how we're going to measure angles in these angles of incident and angle of reflection. In a flat or plane mirror, those angles will be the same. The angle of incident will be the angle of reflection, and if you were to graph this algebraically, you'd use an absolute value function to model these bouncing rays off of a flat surface like that. Now the truth is, when you have a rough surface, like over here on the right, you're not going to get that nice, consistent, pretty reflection, so things will start to get distorted. Rays of light won't converge to the same area. And so because of that, you end up with a very blurry or imperfect image. However, it does allow us to see the light from the source in different locations. You can see here in picture A versus picture B, if the source of light comes down and it bounces at random different angles because the surface is so rough, then there's going to be more areas where we can gather that light, if you will. But on a smooth surface, that light will all reflect the same way, and if you're not in that parallel path, you see nothing. And that's why we can get, for instance, if I take a shiny watch that you might have on your wrist, and I get the reflection of the sunlight off of that and shine it towards someone's eyes, in that specific area, I can I can make their eyes dilate or contract as they try to shade themselves from the sun or from the light that's coming off that watch. I could do that with my watch, but if I have a rough surface, it's not as focused, but it's also going to spread out to a bigger area and be that way. All right, so a couple things we need to understand. When we look in a flat mirror, okay, we have the physical object. So we're gonna talk about this guy that's the actual bottle, whatever this is. I don't know what they're calling this, but this right here would be called an object because it's real. It exists in our own space. This thing over here that we look at, when you look in a mirror, you're not looking down at the object. You're actually looking through the mirror to where the object appears to be. This over here was what we would call the image of the object, right? It's a reflected image. Now, if we wanted to calculate certain things like how far away is the image behind the mirror, we would say that that image distance, that's what DI stands for, would equal the object distance, that's what DO stands for, if we're talking about a flat mirror or a plane mirror. Now we can use these angles of incident and reflection to use basic geometry to figure out, how large the object would be, or the image would be relative to the object. Is it minimized? Is it maximized? It's further away, but how big is it relative to the other object, to the original object? So we have DI for image distance, DO for object distance. Now, a couple of things that we need to understand. If the image occurs behind a mirror, okay, which it will in a plane mirror, we consider that image to be a virtual image. A virtual image just means that you couldn't put paper or some sort of film behind it and have it display on that. So if I put a screen right here, right, for that light to project onto, it would never actually show the image of the pill bottle or whatever this is, this bottle, because it's not really there. Its location isn't real. It's a virtual or imaginary location. However, if that reflected image actually occurred over here on the same side of the mirror that we started on, we would consider that a real image, and it would be something we could actually put some paper right here, and we would be able to see an image displayed on the paper itself. When we get the lenses and mirrors out in class, we'll have a chance to look at those and see some clever things. When it comes to seeing, yourself in the mirror, something to kind of keep in mind, right? So the top of my hairline, it comes down, and it comes down to my eye like that. Well, where did that ray of light appear to come from? It appeared to come from back here. And so I can see, there's the top of my head. Now, if I look down towards my feet, you'll notice I don't actually look at the bottom of the ground. I actually just look, basically halfway down. And halfway down would get me to my toes. But where does that appear? Well, I guess, and that's a reflected light, right? So the reflection off my toes bounces off the mirror and goes up to my eyes. But where did it appear to come from? What appears to come from down here? And so in the mirror, I would see a full body image, even though the mirror is not as tall as I am. So kind of a cool reality. You take a mirror and you pull it back from yourself, you don't see more of yourself. You see a smaller version on that mirror because you're further away, and our observation of height and things like that shrinks over distance. But what's really cool about it is because of the angles, if a mirror is half your height, you can see your whole body from head to toe in that mirror. Anything bigger than that, you'll start to see the ground or you'll see the sky above your head, but you won't see more or less of yourself. Now, when we talk about object and image distances, things like that, real versus virtual, on a plane mirror, everything is virtual. The object distance is the image distance. But as soon as we start to curve our mirrors, we start to have different effects take place. And you can, if you're at home, you go home today, you can pull out a spoon and look at the front of the spoon, the back of the spoon, and you can see in your reflection the differences there. A lot of you, if you're someone who has a mirror, like a makeup mirror, a compact mirror, you'll see that those two mirrors are slightly different. One of them is probably a flat mirror, the other is probably a convex mirror to make it so you can see up close a little easier. So a couple of things we keep in mind. A convex mirror, okay, it pokes out at you. So all the light is going to hit the curved the outward curved surface, and it's going to bounce off of that curved surface. And what it does is it doesn't curve. It doesn't, you have to realize that it's at the perpendicular, right? So all of these angles of incidence and reflection, they're different depending on what the curvature of the lens is, or the mirror is. And this is what we have, a concave mirror, where it's caved in towards you. This would be the inside of the spoon. This would be the back of the spoon up here for our convex. And we get different views, okay? I guess a concave mirror for our cosmetic mirrors, my bad. And those convex are going to allow us to see a wider variety of things. All right, so a couple things that we need to understand, that there is a focal point for all of these mirrors. Now, if you send parallel light in, they all bend towards a specific point. That specific point is called the focal point, okay? And that focal point has a very specific location relative to the curvature of the mirror. If you thought of this mirror as a big sphere, right, that went around and completed a sphere, and the center of the sphere was right here, the focal length would be half the size of the radius of curvature. And so we have our first formula that we need to understand. For a curved mirror, the focal length, or the point where everything would focus in, is equal to half of the radius of its curvature. Okay. Let's see, what else do you need to know right off? All right, so now we can do some ray diagrams. All right, these ray diagrams are really important that we understand how to draw them for the sake of being able to physically model what the light is doing in a ray diagram, or with it when it bounces off a mirror. Now, there are 3 rays we always draw. Okay, and I'm going to try to identify those 3 rays right here and make sure you're clear about what they are. Ray 1 goes from the object, from the tip of the object, parallel to the axis. Right, so you can see we're coming along, we're going following the x-axis, parallel, right? When we hit this mirror, we're going to bend and go through the focal point. Oops, I missed the focal point, but through the focal point. And that's ray number 1, okay? Now, if this first line isn't parallel to the x-axis, we're going to get a wrong answer. If we don't go through the center of the focus, we're going to get a wrong answer. So it's important that we're really clear about getting this drawn as perfectly as we can when we're asked to draw a ray diagram. Ray number 2 is going to start by going through the focal point. It's going to hit the mirror. When it hits the mirror, it's going to bounce out parallel to the x-axis. So it came down to the mirror, but by going through the focus, doop, and then it bounces off that mirror, and it's got to be parallel to the x-axis there. Okay. So the first one is parallel, then bounces through the focus. The second one is through the focus and bounces off parallel. The third one is our way of just confirming that we haven't messed this up. And the way that we do that is by connecting the center, okay, of curvature with the top of our object. So if you look at it like this, object, top of the object, center, and we do like to include the mirror here, but if we draw a line that connects those 3 points, you'll notice that all 3 rays end up in the exact same location down here. That this spot right here, we have all 3 rays pointed in the same location. That means that is the tip of my image. I'm going to reflect this down, right? Okay. So a couple of things to notice. One, it's upside down. When it's upside down, we call that inverted. Next thing we might look at, hey, it was real small before, it seems a lot taller now. We'd call that magnified. Okay, magnified or minimized. And the other thing is, because I could actually put a physical screen right here, and the object or the image would reflect onto that from the mirror, we would call this a real image. We would call it a virtual image if it existed behind the mirror, because you can't actually get the light back there. but all of the light does physically come to this location. This is what's called a concave mirror. And we'd have all that light brought to us. Okay. If we tried the same thing with a convex mirror, let me see if I can come down here and find a convex mirror. Well, there's some more examples of the convex mirrors we'll get to in a second. Let's finish this up with some specific calculations. Okay, if we want to make a prediction about things like how tall or how far away is the image, what's its image distance compared to where it was before, where's its actual location, or how big is it? Is it bigger or is it smaller? There are these different measurements we can take. The height of the object would be called HO. The height of the image would be called HI. F is our focal length. DO is the object distance. And DI is the image distance from the lens to the image. If we take those specific measurements, we end up with these specific formulas. The height of the object divided by the height of the image is equal to the distance to the object divided by the distance to the image. That also, if we flip that, we can get the magnification. Is it twice as big? Is it half as big? Can be found by this formula. HI over HO, or negative DI over DO. And the negative in this formula is there because if your object is on the same side as your image, there's a negative there, and we have to be careful about our sign conventions in terms of what's positive and what's negative. The other thing that we need to have is this mirror equation. We'll see this equation used in lenses and in mirrors, but this allows us to relate a predicted image distance to our object distance and our focal length. If we know the focal length and we know how far away our object physically is, we can predict where the image will occur. And it's 1 over DO plus 1 over DI equals 1 over F. All right. Now, when we bring the object closer than the focal point, it starts to make a difference, like this here. When we bring our object inside of the focal point, you see how it's closer than the focal point? Something different starts to happen. Okay, so think about bringing your face close to a compact mirror for your makeup. Okay, you wanted to see those nasty blackheads that you've got, or see if your pores are clean. All right, so this would be, pretend this is something that you're putting close to that mirror. Now we can go from here parallel. There's ray 1 parallel, and then we bounce back through the focal point. Okay, so there's ray 1. We can see that being drawn. Okay, ray 1 there, and then down through. Ray 2. Okay, notice I can't go down to the focal point and hit the mirror, but I can sort of create an imaginary pathway from the focal point across the tip of the arrow to the lens, and then I should bounce out and come out parallel. Okay, so remember, we go parallel to the focal point to parallel. Well, you might notice right now that these two rays are not going to match up on this left side of the lens. They're never going to hit the same point, so they can't converge there. And the third one, of course, is the center, the tip of the arrow, and the mirror, which would be right here. Okay, it would hit that, and it would actually bounce right back down. Well, that means that in all of these rays, they never all three meet in the same point on this side of the mirror. But if I backtrack where they appear to be coming from, in terms of what my eye sees, okay, I can find a single location where the image appears to be coming from. So this is an example of being too close to the mirror and creating a virtual image. But a couple things to keep in mind. It is upright. Instead of being upside down like the other one, this is upright, and it's a lot bigger. So if I want to look at something close, bringing it inside the focal length is going to magnify that image. Okay? And so I'm going to be able to look at this a lot closer than I could to the naked eye. Like, this guy is small, but in the reflected image, it's a lot bigger. Okay? And so that's a benefit to having these. Now a convex mirror has some similar attributes. Okay, we still use the same general rules for measuring object distance and image distance. Focal length, however, because it's on the back side, the focal length is going to come out negative. Let's look at the rule or sign conventions that we need to identify as we do these ray diagrams. Okay, even though you can make an analytic calculation, you should always do a ray diagram to see what you're thinking about. Even if you don't do a perfect job, knowing, okay, where should the light be? Am I going to get a virtual or a real image here? Things like that. They matter. Okay, you can apply your mirrored equation. The 1 over dO plus 1 over di equals 1 over f. A couple of sign conventions. When the object, image, or focal point is on the reflecting side of the mirror, okay, usually on the left, the distance is positive. If any of these are behind the mirror, we consider them negative. That's why a convex mirror has a negative focal length. Okay. The height is positive if the image is upright, and negative if it's inverted. All right. So a couple of those rules. Remember, if you're on the left side of the mirror, you're positive distances, and if you're on the right side of the mirror, you've got a negative distance. All right. Hopefully that's enough to help you guys be successful on the problems that you have there. Read through the problem. You've got this as your basic problem building structure. Okay, if I go into the chapter 23, sorry, I got to get back in here. If I come to 23, come down to the homework problems back here. For instance, I've got a spherical mirror, a concave mirror pointing at the sun, focuses the rays. So that focus is the sun's rays, that's 18 centimeters. Okay, what is the radius of the spherical surface? Well, if the focal length is 18 centimeters, you should be able to figure out the radius from there because of the relationship there. Here we've got some basic reflections. You know, as that's a 40-degree angle, what are these angles here to be able to figure out that angle there? Using your basic geometry, same thing here. Use some basic trigonometry. Okay, how far out will I see if that's 43 centimeters? And I know that you know these angles here are the same. On a plane mirror, these two angles would match. So how big are they? And if they're that big, can you use some right triangle trigonometry to figure out this distance here? If you know this is 43. Okay, so given some of that information, you should be able to figure out your thetas. You're going to have to do two triangles probably. Right, there's the triangle for the top, and there's a triangle for the bottom, but they both have the same angles. So you should be able to use that to solve the problem. Good luck. I will see you guys in class and answer lots of questions, but you should be working on this stuff, doing the best you can with the time that you have. All right? Good luck. We'll see you in class.